So example 11 is actually an example that we already did in class. So you're asked to calculate the delta G for the reaction of iron and oxygen gas forming iron 3 oxide. So what I want you guys to do, notice you're given the delta H of formation and the molar entropy. So I actually want you to try this. See if you can use the delta H and the delta S values to find Gibbs free energy, and then when you're done, come back and look at the answer and see if you got it right. Okay, so you can take a look here at what you should have gotten for your free energy of this process. Again, when you have delta H and delta S, you're going to use equation that we've been looking at. Again, it's on your AP equation sheet. Delta H and delta S are both found the same way, products minus reactants, and take into account coefficients. For delta H, notice iron and oxygen are both 0 because they are in their elemental state. However, that is not true for entropy. Again, like we talked about in class, make sure you pay attention to your units and make your units equal, and then just give units on your final answer. So once you go through and you solve and you plug everything in, and you weren't actually given the temperature, but if you're given these heat of formations and the entropies, that's at 25 degrees Celsius. So then just plug in 25 degrees Celsius or 298 Kelvin to get negative 1,490 kilojoules. Now, with this, delta G is less than 0. What does this tell you? It tells you that it's spontaneous. And now I want to go through another example looking at spontaneity and predicting signs. So this isn't actually in your notes, but you can add it to the back or in any extra space that you have. So the Haber process for the production of ammonia is given in this reaction. And assume that delta H and delta S for the reaction don't change with temperature. So what that means is we don't have to worry about temperature affecting those values when we're looking at delta G. So part A says to predict the direction in which delta G for the reaction changes with increasing temperature. So we want to know, as temperature increases, what happens to delta G. And so what we can do is we can actually predict the sign first of delta S. And then we can look at the equation that we've been looking at this entire time and go from there. So to start out, let's just look at delta S, because we can determine delta S, or at least the sign of delta S, just by looking at the reaction. So on the reactant side, we have 4 moles of gas, and on the product side, we have 2 moles of gas. So what is happening to the entropy? Delta S is less than 0. So less than 0, right? Because we are increasing the order. So if we take a look at part of the equation that is minus T delta S, let's figure out what this means. If delta S is negative, that means that we're adding that to your delta H. Alright, so we're not even worrying about what the sign is of delta H right now, because we just want this qualitative, and it just wants the direction of delta G. Okay, so because delta S is negative, that minus T delta S becomes positive, okay, because negative times a negative is a positive. And that means that as temperature goes up, right, as this T goes up, what's going to happen to this positive value? Well, it's going to become more positive. Okay, so as temperature goes up, that portion of this equation up here is going to become more positive. And if that becomes more positive, that means that's also going to be your effect on delta G, right? If T delta S becomes more positive, then your delta G is also going to become more positive or less negative. So you can either say more positive or less negative, right? So the driving force of this production of ammonia becomes smaller as temperature goes up. The reaction is going to become less spontaneous as temperature goes up. And so now part B says to calculate delta G at 25 degrees Celsius and 500 degrees Celsius. So in order to calculate this, you need delta G equals delta H minus T delta S. And so to solve for this delta G right here, we need both delta H and delta S. So what you're going to have to do is look in Appendix C, solve for both delta H and delta S for that reaction, and then once you have that, plug in your temperature for T. So instead of 25 degrees Celsius, it's going to be 298. So you plug in delta H, which is negative 92.38 kilojoules, and delta S, which is negative 198.3 joules per Kelvin, which means make sure that you convert. And again, we're assuming that those don't change with temperature, which means we can calculate delta G at any temperature using this equation. And so what I found is that delta G for 25 degrees Celsius is negative 33.3 kilojoules. Again, that's for 25 or 298 Kelvin. And at 500 degrees Celsius, that's 773 Kelvin, I found the delta G to be 61 kilojoules. Okay, so again, at 25 degrees Celsius, it's negative 33.3, and at 500 degrees Celsius, it's 61 kilojoules. So notice that increasing the temperature from 298 Kelvin to 773 Kelvin changes delta G from negative to positive. Okay, so again, we're assuming that delta H and delta S don't change, and from that we notice that delta G goes from negative to positive. That goes along with what we predicted in A. Okay, so what that means is at a lower temperature, this reaction is spontaneous. At higher temperatures, it is non-spontaneous. So those are the types of qualitative questions. Now I know this last part wasn't qualitative, but these are the types of qualitative questions that we're going to look at. It takes a lot of thinking. So you have to, again, take a step back and actually think, use your signs, just memorize that table. Okay, memorize that table and you'll be perfect for this. So write down any questions that you have. We'll go over more of these examples just to make sure that you've got them, and to go over any questions that you might have on different examples. And then we just have one more section after this in this chapter.